Hello friends, myself Ankush Gupta here at the Gate Coach, and in this video we are going to discuss the solution of process calculation subject. All the questions came from the process calculation subject in Gate 24 chemical engineering paper. So there were total 3 questions this year from process calculation for 5 marks. 2 questions of 2 marks and 1 question for 1 mark. So let's start with 1 mark question, which was this question number 31 here on your screen. And like every year, this year also all 3 questions were very easy. Means if you just read the question, you will get the answer like that. Okay, so first question. Consider the reaction N2 plus 3H2 gives 2NH3 in a continuous flow reactor under steady state condition. The component flow rates at the reactor inlet are. If the fractional conversion of hydrogen is given, then what will be the outlet flow rate of nitrogen? They are asking. So it is very easy. So you can see from the reaction. Okay. Amount of hydrogen reacted will be hydrogen fed into its conversion. So that is 300 mole per second multiply by 0.6. So amount of hydrogen reacted will be 180 mole per second. Okay. And from the reaction it is obvious that 3 mole hydrogen react with 1 mole of nitrogen. So you can see 180 mole per second of hydrogen will react with 1 by 3 into 180, that is 60 mole per second of nitrogen. So nitrogen leaving in the reactor, nitrogen out will be fed minus reacted. That is 100 minus 60 equal to 40 mole per second. Simple. Okay, so this was for 1 mark. Now the other 2 questions for 2 marks were. (54) and 55. Question number 54. This one. So like here in this question it is given that consider the process in the figure for manufacturing V. The feed to the process is 90% A and a closed boiling inert component I, doesn't matter, inert simply. Particular steady state some data is given and they are asking what will be the flow rate of A in the purge stream. So this was your block diagram given. If you see, some people might get kind of a fear, oh, such a difficult question, what a diagram. But if you look at the diagram closely, you can easily draw that. You can simplify this block diagram. And the block diagram will be the same which we were using in our practice sessions. Okay, so you can draw the block diagram something like this. This is the reactor. Reactor outlet going to a separator where this pure B is produced as a product and some stream was recycled, where they split some recycle stream as purge, and this is the recycle stream. So we can consider this as fresh feed and this part going in the reactor inlet as mixed feed. Okay, so as per our common notations, let's name the streams. This is fresh feed F, mixed feed M, recycle stream R, purge stream P, product stream N, reactor outlet G, and this is total recycle stream T. Okay, and the basis will be this given 100 moles of B, 100 moles, 100 kilomole per hour of B produced. Okay, kilomole hour of B produced here. N is equal to 100. So if you look at this diagram, on this side or the simplified version, doesn't matter, both are same. So you will realize one thing, that in purge stream there is no B. And here we are just doing the splitting. So it is obvious that the composition of all these 3 streams will be same. That is T stream, P stream and R stream will be same. So it means there is no B involved. B is not there in any of these. So what will be there? And here only pure B is leaving in the N stream. And what we will have in reactor outlet possibly, reaction is given as 2A gives B. So it is obvious here we will have some A unreacted, because you can see single pass conversion is 50% only. We will have inert, which is coming from the feed, and we will also have B as a product. So in this T stream also we will have only A and I. In recycle stream also we will have only A and I. In purge stream also we will have A and only I. Nothing else. Simple. So anyways, I can solve this question directly for you in just 2 lines, but I am explaining so that you can understand if you have any problem, like how to approach this question. Still, if any of you have such issue. Okay, so here, let's do the mole balance. I have told you whenever we choose the basis, always start your calculation from that side. Okay, so we have taken the basis on product side, this. So we will start our calculation from this side. So right to left. See, 100 moles B is here. B is not going anywhere else. So it is obvious the amount of B leaving in N stream and amount of B entering in G stream will be same. So here also we will have 100 kilomole per hour of B. Okay. Now what? After that just came to the reactor. I have told you so many times in the class. If you are stuck, you don't know what to do, always go on the reactor. 90% times you will get your answer from there only. So over reactor, when we go, we have inlet stream, that is M stream. We have outlet stream, that is G stream, reactor outlet. So in the inlet stream, we will have A, we will have I only, because recycle has AI, feed has AI, given 90% A, 10% inert in the fresh feed. And in outlet, we will have A, I and B all. B is same, 100 kilomole per hour as produced. Okay. So over the reactor. Generally, this type of question we have done so many times in the classes, but there we were used to have composition at the mixed feed or at the fresh feed. So here in the fresh feed it is given, but we don't need to use that, because simply we can say amount of A in the mixed feed is, let's say, MA, kilomole per hour. Okay, and single pass conversion is 50%, so it is obvious amount of A reacted will be fed into conversion, this. So amount of A unreacted will be, or you can say amount of A leaving in the G stream, MA into 0.5 kilomole per hour. Okay, and if you look at the reaction, it is obvious 1 mole B required 2 mole A. So how many B we have? 100. So 100 kilomole per hour of B will require 200 kilomole per hour of A. That means moles of A reacted, this must be equal to 200 kilomole per hour. So that means amount of A fed was 400 kilomole per hour. So it means amount of A leaving in the reactor outlet will also be 200 kilomole per hour here. Okay, this A is not going here, this A is going on this side only. So whatever A is there in G stream, the same amount of A is there in T stream, 200 kilomole per hour. Now on the splitting point, if you do the balance over component A, so you can say A in T stream equal to A in recycle stream plus A in purge stream. So A in T stream is 200 kilomole per hour. A in recycle stream will be total flow rate of recycle stream R into mole fraction of A. Let's say that is XA, or to be precise, XRA. Mole fraction of A in recycle stream, XRA. And the same will be there in purge and T. The amount of A in purge stream will be total amount into mole fraction of A. Okay. And here it is given that recycle to purge ratio is 10. That means R equal to 10 times of P, which you can put here, and you will get 11 times of XRA. So your answer will be, it's not 11 times of XRA, it is 11 times of P into XRA. Okay. So from here, you guys can see P into XRA will be equal to 200 upon 11, that is 18.2 approx. P into XRA means a total amount of A in purchase stream. That is the answer. Simple. 2 marks question. Okay. So I hope it is clear. Now let's move to the next question, which was one interesting question. Easy but interesting. Okay. If you look at the statement from outside, you will find it difficult. What are these equations? What is RHR? But if you read the statement properly, you will get the answer. Methane combusts with air in a furnace as CH4 plus 2O2 gives CO2 plus 2H2O. The heat of reaction is given minus 880 kilojoule per mole of CH4, which is constant. The furnace is well insulated, means adiabatic condition. No other side reaction is there. All components behave as an ideal gas and with constant molar heat capacity. So heat capacity of the mixture or heat capacity of the component is same, which is 44 joule per mole per degree Celsius and constant. Air may be considered as 20% O2 and 80% N2. You can understand from this data only. Generally, air has 21% O2 and 79% N2, but in this they have given 20-80. So it is obvious they want us to simplify the calculation. Okay, so these are the hints they give with the questions, if you can catch. Okay, so the air fuel mixture enters the furnace at 50 degrees Celsius. So suppose this is my furnace, which is perfectly insulated from all the sides. So we can think like this: air and fuel mixture is entering at a temperature of 50 degrees Celsius. Okay. The methane conversion is given, varies with the air to fuel ratio as this, R as this, where RS is the stoichiometric amount of air and stoichiometric ratio of air to methane, and R is 1.05 times of RS. So you calculate RS, then you will get R, then you will get X, and then we will see what we have to do. So here for RS, for stoichiometric calculations or anything we can do, but first let's take the basis as 1 mole of CH4 fed. Okay, so the stoichiometric calculations you can see, stoichiometric calculations from the reaction, you can see that 1 mole CH4 required 2 mole O2. Since air has, or you can think like this, O2 in air is equal to amount of air into 0.2. So amount of air will be O2, that is 2 moles divided by 0.2, that is 10 moles. I hope you do understand this, all this stuff. So RS will be amount of air to the methane, that is 10. So R will be 1.05 times of RS, that is 10.5 mole. So you guys can see, if R is this, so that means amount of air fed. Now we will do the actual calculations. This was the stoichiometric calculation, now the actual calculation. Amount of air fed will be 10.5 mole, because CH is 1.5, 1 mole only. So air fed is this. So O2 fed will be 10.5 into 0.2, that is 2.1 mole, and N2 fed will be 10.5 into 0.8, that is 8.4 mole. We got this part. Now we will see the amount of the components in the outlet. Okay. So for that we need to find out the amount of CH4 reacted. So we need the value of X. So you can see we have X equal to 1 minus 0.1 times of e to the power minus 2 multiplied by R minus RS, that is 10.5 minus 10. So when you solve this, you will get X equal to 0.9632. So that means amount of CH4 reacted will be fed into conversion. Fed into conversion. So Fed is 1, conversion is 0.9632. So CH4 reacted will be 0.9632 mole. Now O2 reacted. O2 reacted will be, you can see the reaction, 1 mole CH4 required 2 mole O. So 0.9632 moles of CH4 will required 2 into this. That is 1.99264 moles. And from the reaction itself, you can see CO2 formed will be 1 mole CH4 gives 1 mole CO2. So 0.9632 moles of CH4 will give 0.9632 moles of CO2. 1 mole CH4 gives 2 moles of H2O. So 0.9632 moles of CH4 will give 2 into this, that is 1.9264 moles of H2O. So that means total moles leaving, let's say N, will be, total moles leaving, let's say N, will be all these moles. CH4 remaining, O2 remaining, plus CO2 formed, H2O formed, and nitrogen fed. So CH4 remaining will be fed minus reacted, that is 0.0368 moles. Oxygen remaining will be fed minus reacted, that is 2.1 minus this, equal to 0.1736 mole. So final moles leaving will be nitrogen leaving, CH4 remaining, oxygen remaining, CO2 formed, H2O formed, that is 11.5 mole. And here if you guys see, total moles fed, total moles fed, that is N naught, let's say, air fed plus CH4 fed. We don't need to break down O2 and N2 separately. We can directly say air. So air fed is 10.5, CH4 fed is 1, let's say N naught, total moles fed. Air fed 10.5 plus CH4 fed 1, that is 11.5 mole. So it is obvious that total moles entering and total moles leaving are same. I hope everything is clear till this part. Now just energy balance and you will get your answer. So I am clearing all this. If you want to see, you can check, pause the screen and you can see again. So energy balance will be like total energy in minus total energy out is equal to total energy change due to reaction. Okay, so here you guys can see total energy in due to air, CH4, that means total moles entered, Cp of mixture multiplied by T1 minus T0. So here total moles entered is 11.5. Cp of mixture is given 44 joule per mole per degree Celsius. T1 is 50 degrees Celsius given. T0, they haven't said anything about the reference temperature, so we will consider that as 0 degrees Celsius. So a total energy in, here you guys can check, will be 25,300 joule. Okay. Similarly, you can do it for energy out. The total moles leaving and Cp of mixture, then final temperature, let's say T2 minus reference temperature T0. So here when you will put the value 11.5 into 44 into T2 minus 0, so you will get 506 times of T2 joule. And energy change due to reaction will be moles of CH4 reacted into delta H. Why? Because delta H is given in the terms of kilojoule per mole of CH4 reacted. So moles of CH4 reacted is 0.9632 and delta H is there in minus 880 kilojoule, which you can convert into joule like this. Okay. Now when you will put all these three values in the equation, you will get your answer. So it will be like 25300 minus 506 times of T2 equal to minus of this. What is that value? That value is 847616 minus of 847616 joule. You can check. So after solving this, you will get T2 approx 1725 degrees Celsius. To be exact, 1725.13. They are asking up to 1 decimal place, so you can write 1725.1. You were supposed to write. Okay, so that's all for the PC. Stay tuned here. We will upload the videos subject wise for all the questions related to GATE 24 chemical engineering paper. So see you guys. Take care. Bye bye.